This presentation is a general overview about the LLVM compiler. We're making this as a part of an assignment towards the compiler's course in an institute. Let's start with some historical background. The LLVM project started under Victor Vikram Adve and Chris Latner at the University of Illinois, Urbana-Champaign. The project started out in 2000, and by 2005, Latner was hired by Apple to work on LLVM systems for use in various Apple development systems. The project started out as a research into dynamic compilation techniques for static and dynamic programming languages. So, following is a list of high-level languages supported by LLVM: Ada, C, C++, DLang, Delphi, Fortran, Haskell, Julia, Objective-C, Rust, and Swift. So now Pranav will be discussing the schematic of the architecture of LLVM with you.
Right. So the immediate observation we can make by looking at this image is that this compiler is divided into three distinct parts: the front end, the optimizer, and the back end phases. The front end phase is the phase through which we feed our source code into the compiler. As you can see, the LLVM compiler can support a number of front ends. For example, as you can see over here, C, Fortran, and Haskell. This front end generates an intermediate representation which we call LLVM IR, and upon being optimized by the LLVM optimizer, it is then fed into the backend. To get a better idea as to what is happening within the compiler, as we can see in the next slide, the object files of each generated by each front end are linked together by the LLVM linker, and it is then passed through the optimizer. So if we go back to the previous slide, we can see that this intermediate representation is sent to each and every single backend. So in this case, the same intermediate representation is sent to the x86 backend, the PowerPC backend, and the ARM backend. And each backend produces its own corresponding machine code. Now, Bharat will go into how each of these phases function.
Yeah. So the LLVM compiler can be broadly separated into three phases: the front end, the optimizer, and the back end. The front end is responsible for taking in source code, validating it, parsing it, diagnosing errors, and converting it to something called LLVM intermediate representation or LLVM-IR. So usually, but not always, the front end builds an abstract syntax tree and then converts it into an LLVM IR. LLVM IR is a text representation and it is a complete code representation. A complete code representation means that there is no information lost from the source code to LLVM IR. Any loop, variable, algorithm process in the source code uh, is going to be a part of the LLVM IR. LLVM IR is also the only interface between the front end and the optimizer. It means that it's the only thing that connects the front end and the optimizer. There's nothing else involved. Moving on to the optimizer, it takes in the LLVM IR as an input and generates another LLVM IR. The optimizer is built as a series of passes, which include but are not limited to the inliner pass, expression reassociation pass, loop invariant code motion, etc. Now this LLVM optimized LLVM IR is now sent to the backend. The backend, which is also called as the code generator, takes in LLVM IR as an input and produces the corresponding native machine code. Even the backend is built as a series of passes with a few default built-in passes. Now these passes, default passes, can be overridden and overwritten based on the choice of the target architecture. So now Pranav will be discussing the strengths and limitations of the compiler with you.
Right. So one very important thing which we can make note of is the fact that this compiler is modular in nature. What this means is that the users can swap out different parts of the compiler and change it to match their needs. This property makes the compiler very flexible, and developers can easily modify the compiler to make what they're working on far more easier and change the components according to their needs. As we saw before, this compiler supports a number of front end interfaces and back end APIs. The LLVM IR can also be converted into different forms such as text, memory, bitcode, etc., and back as well. The LLVM source code is also more accessible than other compilers. So in case any research needs to be done on this compiler, it can be done quite easily. Developers also have more freedom with respect to what they want to do with the code. Instead of being strictly restricted to business applications or corporate applications, this compiler can be used for personal projects as well. Going on, going on, the compiler also includes an aggressive optimizer, which includes scalar, interprocedural, profile driven, and some simple loop optimizations. This compiler is also being developed and updated regularly. The last build of this compiler was released just a few weeks ago, going to show how often it is used in today's world. It also supports garbage collection. All these positives in mind, however, it does have its few limitations. Back on the point of garbage collection, the garbage collector in the compiler has to be provided and it's not readily available with it. Furthermore, this compiler is relatively new as compared to old compilers such as GCC. As a result, this compiler is more prone to being buggy and it does not have the same maturity as other compilers. When we say maturity, we mean, you know, prone to being bugs and other stuff like not supporting as many languages, architectures, and operating systems. Another point which we came across while researching this compiler was that there have been occurrences where this compiler has failed to make successful builds of Debian packages. Although the value is 5%, it is still something to be noted. Now, what it will explain what are the backends supported by this compiler.
Right. So as you can see, a lot of backends are supported by the LLVM compiler. They are the ARM backend, Qualcomm Hexagon, MIPS, NPTX, PowerPC, AMD Terascale, GCN, Spark, Z Architecture, x86, x86-64, and Xcore. So we also did some snooping around for compilers in general. Compilers are needed in a lot of different scenarios. They're needed in small devices like mobile phones, embedded systems like drones, IoT systems, and parallel programming systems as well. A few examples of compilers for embedded systems are Small Device C compiler, ComCert Kyle. Borland Turbo C is used for compilers used for graphics, while Rose is a fairly popular compiler for parallel computing.
The usage of compilers also extends to the realm of game development. LLVM and Clang are used as compilers in the Nintendo Switch and the PlayStation line of consoles. Microsoft uses their own personal compiler, the Microsoft Visual C++, as a compiler for games on their flagship console, the Xbox. And Green Hills is a company which provides technological tools, and some of the compilers have been made use of in the 3DS line of consoles. So that more or less concludes our presentation. If you want to get a source of where we got our information from, provided over here are some of the links, and you can access these links through the description. We'll be leaving a link to the presentation. And that wraps up our video. These are the following members of our group who worked on this presentation, and we would like to thank you for taking your time out and listening to this presentation. Thank you.